Thanks to the organizers for the opportunity to give this talk. This is a joint work with Francesc Fité. And in order to give some motivation for the main result that I will explain, I'll begin by talking a little bit about the conjecture of Coleman that sort of gives a general framework for the problem that we study. So this is a conjecture on endomorphism algebras of abelian varieties. So this is a notation I will use. If A is an abelian variety defined over a number field K, I will denote by n q bar 0 of A the algebra of q bar endomorphisms of A. So the algebra of endomorphisms defined over the algebraic closure. And if G and D are positive integers, script A sub G comma D will denote the set of q bar endomorphism algebras of abelian varieties of dimension G, which are defined over some number field of degree D. This set taken up to isomorphism. And then the conjecture of Coleman is that A sub G comma D should be finite for any G and D. That is to say, even though there are, of course, infinitely many abelian varieties of dimension G defined over some number field of degree D, they should give rise to only finitely many endomorphism algebras, or geometric endomorphism algebras. So this is one version of the conjecture. There is an even stronger version of the conjecture which states that the set of endomorphism rings should also be finite, but this is stronger in the sense that there can be abelian varieties with different endomorphism rings that when you tensor them with Q, you get the same algebra. So there are more endomorphism rings than endomorphism algebras, but still the expectation is that they should also be, there should also be finitely many. But we'll stick to the version of the conjecture for algebras because this is already hard enough. Actually, very little is known about this conjecture, but some things are known. For example, the one-dimensional case is known, the case of elliptic curves. I'll give you the proof in the next slide, but it's an immediate consequence of the theory of complex multiplication, together with the fact that there are finitely many imaginary quadratic fields of bounded class number. Another case that is known is the case of CM abelian varieties. So if we restrict to abelian varieties that have CM in the sense that their endomorphism algebra is a number field of degree twice the dimension of the variety, then this set of CM endomorphism algebras is known to be finite for any G and D due to this fairly recent result of Oren and Skorobogatov. And we're interested in this talk in the case of dimension 2, so abelian surfaces, and degree 1. So abelian surfaces defined over Q, so it's sort of the next case in difficulty after the case of elliptic curves. But before going to the case of abelian surfaces, let me talk a little bit about this one-dimensional case of elliptic curves. So if we have an elliptic curve defined over a number field of degree D, then the possibilities for the Q-bar endomorphism algebra, of course, are, well, it is either Q if the curve doesn't have CM, or it's an imaginary quadratic field, call it M, if the curve has CM or potential CM. Now, as we've already seen in previous talks, we have this very good theory of complex multiplication. So we know how to construct elliptic curves over the complex numbers with CM by an imaginary quadratic field. We can start with a fractional ideal in this imaginary quadratic field. And if we view it inside the complex numbers, this is a lattice. And C modulo this lattice is an elliptic curve with endomorphism ring the maximal order of the imaginary quadratic field. And then the theory of complex multiplication tells us that there is a one-to-one correspondence between the set of elliptic curves with CM by the maximal order of an imaginary quadratic field and the set of fractional ideals in M modulo scalar multiplication. That is to say, there is a one-to-one correspondence with the class group of the imaginary quadratic field. And using this, one shows that if a curve has CM by the maximal order, then the J invariant is an algebraic number, and well, the field it defines over Q has degree equal to the class number. This is if it has complex multiplication by the maximal order. If the complex multiplication is by some smaller order, then, well, the field defined by the J invariant has degree at least the class number of the imaginary quadratic field. And this is the key for showing the finiteness of the M's that arise here, that can arise here, because if we have an elliptic curve over a number field k, then the field generated by the J invariant is contained in k, and by this inequality, then the class group of M is bounded by the degree of the number field, that is bounded by D, which is fixed, and we know that there are finitely many imaginary quadratic fields of bounded degree. Okay, so this shows that this set A1, D is finite for all D, but in this case, we know actually what these sets are explicitly, or at least for many values of D. So for example, Mark Watkins computed all imaginary quadratic fields of class number D for D up to 100. So we know these sets A1, D explicitly, at least for these values of D. So for example, of course, A11 is the list of imaginary quadratic fields of class number 1 together with Q. Okay, and now we go to the case of abelian surfaces defined over Q. So this is the set that we'll study in this talk. Well, we'll restrict this set a little bit more later, but A to 1, so this denotes the set of Q-bar endomorphism algebras of abelian surfaces defined over Q. And now there is a dichotomy. So this abelian surface defined over Q can be geometrically simple. This means that it stays simple when we extend scalars to Q-bar, or it can be geometrically split, meaning that over Q-bar it becomes isogynous to a product of elliptic curves. Now the possibilities for the endomorphism algebra, the geometric endomorphism algebra of an abelian surface are also well known. So this is just particularizing to the case of dimension 2, the general classification of endomorphism algebras of abelian varieties, plus some refinements due to Shimura. So the geometric endomorphism algebra can be Q, or a real quadratic field, or a CM field of degree 4, or it can also be a division indefinite quaternion algebra. And these cases correspond to the situation where A is geometrically simple. All these algebras are division algebras. When A is geometrically split, we can have as endomorphism algebra Q times Q, or Q times an imaginary quadratic field, or the product of two distinct imaginary quadratic fields, or M2Q, or 2 by 2 matrices with coefficients in an imaginary quadratic field. Okay, in this dichotomy, the case where A is geometrically simple, so the conjecture is still open. There is one case that we know, the case where we have CM. So this, okay, it's known in general because of this result of Oren Skorobogatov, but in the case of dimension 2, it was known before. Murabayashi and Umegaki, actually, they proved that there are finitely many possibilities for the CM field, and they computed them. They showed that there are 19 possibilities. But for the other cases, namely the real quadratic field or the quaternion algebra, finiteness is not known. So the conjecture is still open in these cases. But we're going to focus on the complementary case. We're going to actually study the case where A is geometrically split. So this, now we restrict a little bit more the set that we want to study. It's this that I'll call A to 1 split, consisting on geometric endomorphism algebras of abelian surfaces defined over Q, which are geometrically split. Okay, now we've restricted a lot the problem, this general conjecture of Coleman. We've restricted actually so much that this set is known to be finite now. This, at least it appears in a paper by Shafarevich in 96. So this set is known to be finite. But okay, our goal is to determine this set explicitly. So we want to know what are the algebras in this set, similarly as we can do in the case of dimension 1. Okay. So let's look a little bit more closely to the to the different decompositions that we can have over Q-bar of these split abelian surfaces, because this determines the endomorphism algebra. So if we have this abelian surface over Q, which is geometrically split, then it can split as a product of elliptic curves which are non-CM. And if I write this, I mean that they are non-isogynous. And if they are isogynous, I write the square of an elliptic curve. And in this case, the endomorphism algebras that arise are Q times Q and M2Q. So, okay, finitely many of them. A can also split over Q-bar as a product of two non-isogynous elliptic curves, in which one or two of the curves can have CM by some imaginary quadratic field. In this case, the geometric endomorphism algebra is Q times an imaginary quadratic field, or the product of two distinct imaginary quadratic fields. I say distinct because there is this theorem that tells you that if two elliptic curves with complex multiplication, they have CM by the same field, then they are Q-bar isogynous. And here I'm assuming that they are not Q-bar isogynous, so the imaginary quadratic fields must be distinct. So here, a priori, we could have infinitely many imaginary quadratic fields arising in this situation, but actually only finitely many arise. And for seeing this, we can apply this result by Vitek, Edlaya, Rugge, and Sutherland. This is a result in their paper where they study satotate groups of abelian surfaces. They prove that precisely in this situation, each one of the elliptic quotients is isogynous to some elliptic curve defined over Q. And then if we have an elliptic curve defined over Q with Cm by an imaginary quadratic field, necessarily the class group of this imaginary quadratic field is 1. And so this gives rise to finitely many options for these M's in this situation. And the third type of splitting that we can have is the splitting in which A becomes Q-bar isogynous to the square of an elliptic curve, which has Cm by some imaginary quadratic field. And here the Q-bar endomorphism algebra is 2 by 2 matrices with coefficients in M. And well, once again, there are only finitely many possibilities for this M. One way of proving this is, for example, this argument. This is the argument that Shefarevich does in his article. He shows that there exists a constant D, a universal constant D, such that all the endomorphisms of A are defined over some number field of degree bounded by D. And to see this, one looks at the action of the Galois group of Q bar over Q on the endomorphism ring of the geometric endomorphism of A. So now I'm looking at the ring of endomorphisms over Q bar. So this has rank 8 over Z because it's an order in M2 of M. And the kernel of this action is precisely the Galois group of Q bar over K. And therefore, the Galois group of K over Q is contained in GL8 of Z. And there is this property of GLN of Z that says that any finite subgroup of GLN of Z is also a finite subgroup of GLN of Z mod 3Z. So the degree of K is bounded, for example, by the degree of this finite group here. So now the decomposition of A as a square of an elliptic curve already takes place over this field of definition of the endomorphisms of A. And since this field has degree bounded by D, this imposes that there are finitely many options for the field of Cm of this elliptic curve E, as in the one-dimensional case. Okay, so this shows that there are finitely many endomorphism algebras, but now the main question is, okay, what imaginary quadratic fields M do appear in this third situation? Okay, which ones do appear and which ones do not appear? And well, here's the main result. So I stated in terms of this set A to 1 split. So the set of Q-bar endomorphism algebras of geometrically split abelian surfaces over Q is made of the following algebras: Q times Q, or M2Q, or Q times an imaginary quadratic field, or the product of two distinct imaginary quadratic fields of class number 1, or 2 by 2 matrices with coefficients in an imaginary quadratic field whose class group is either trivial or C2 cross C2, except from these 6 imaginary quadratic fields listed here. So these 6 fields have class group C2 cross C2, but they do not appear. All the other ones of these class groups, trivial C2 or C2 cross C2, they do appear. So we have explicit lists for these imaginary quadratic fields, and if you look at them and you count how many algebras are there in this list, you find that this set has cardinality 92. Okay, so the first 2 cases correspond to the splitting as non-CM elliptic curves, or the case in which the absolutely simple factors are non-isogynous. And the third case, M2 of M, corresponds to this case where A is isogynous over Q bar to the square of an elliptic curve with Cm by M, and here's where the work is. So here's where we need to prove this result. Okay, so the main question is, okay, I repeat it again here. If we have an abelian surface defined over Q, that we know that over Q bar is isogynous to the square of an elliptic curve that has Cm by some imaginary quadratic field, what are the possibilities for this imaginary quadratic field. And the first restriction that we found is this theorem that we proved with Frances some years ago that says that necessarily the class group of M in this situation is either trivial C2 or C2 cross C2. This is the first crucial restriction. And let me give you a sketch of the proof of this theorem because it's so crucial in what we do. So we look again at the smallest field of definition of all the endomorphisms of A. I'm going to call it K again. And so this field K is where the splitting happens, right? So A over K is already isogenous to the square of an elliptic curve, and we can assume that this elliptic curve is defined over this field K. And on the one hand, the CM theory tells us that this field K is going to contain the Hilbert class field of M because it's a field where all the endomorphisms of this CM elliptic curve are defined, and the CM theory tells us that then K must contain the Hilbert class field. And on the other hand, we have a very good control for the possibilities of the Galois group of K over Q. Actually, we're only interested now in the Galois group of K over M. And again, in this article by Fitek, Etlayer, Rutgen, Sutherland, they classify the possibilities for this Galois group. And it turns out that it can only be a trivial or a cyclic group of order R or a dihedral group of order 2R for these values of R, 2, 3, 4, or 6. This already gives a restriction on the class group of M because, well, the Hilbert class field is contained in K, and these are the possibilities for the Galois group of K over M. So the Hilbert class field is going to be a quotient of one of these groups. So in particular, the Galois group of the Hilbert class field, and in particular, the class group of M is going to be a quotient of one of these groups. So this already gives these possibilities for the class group of M. But we want to show that actually only trivial groups C2 and C2 cross C2 occur. And to do this, okay, so this restriction for the class group of M we obtain by using that E is defined over this field K. But then the main idea to restrict more these possibilities for the class group is to show that actually this E can be defined over some subfield up to isogeny. Namely, we want to prove that there exists some subfield N of K such that the Galois group of N over M is of exponent 2, and E can be defined over N up to isogeny, in the sense that there exists some elliptic curve defined over N, which is isogenous to E when we extend scalars. And then this will prove the result because then, so the Galois group of N over M has to be a quotient of one of these groups, C1, CR, or DR, but the only quotients of exponent 2 of these groups are these C1, C2, or C2 cross C2. And since also the Hilbert class field of M is going to be contained in N, this gives that the class group of M will be one of these three possibilities. And the idea of the proof, of how we prove that the curve E can be defined over this subfield up to isogeny, is to adapt Ribet's theory of Q curves. So a Q curve is a curve that is defined over a number of fields, and it's isogenous to all of its Galois conjugates. And Ribet studied this type of curves in the context of determining the absolutely simple factors of modular Jacobians. But he was mainly interested in the case where the curves do not have CM. So almost all of his results apply for non-CM Q curves. But here we needed some of his results, or analogs of his results, for CM elliptic curves. So we needed to adapt these results to the CM case. And to show you why Q curves arise in this situation, so we have this abelian surface A, which is defined over K. So of course then, for any sigma in the Galois group of K, sigma of A is the same as A, okay? Because A is defined over Q. But then A is isogenous to the square of V, and sigma of A is isogenous to the square of sigma of V. And this shows that sigma of V must be isogenous to E, so we can find for any sigma an isogeny mu sigma from sigma of E to E. And using these isogenies, I mean, we fix one isogeny for every element in the Galois group. We can associate to the elliptic curve a certain cohomology class. I mean, here we're following Ribet, This cohomology class, I'm going to call it C sub P. It's an element in this cohomology group, the H2 of the Galois group of K over M with values in M star. So here the action is the trivial action. And this cohomology class is defined very explicitly. So a cocycle representing it is this function. So C sub P of sigma tau is this composition here. So this is a map from E to E. It's not an isogeny anymore in the sense that we're inverting this isogeny mu sigma tau, but okay, it's an element in M star. Now we're working in the category of elliptic curves up to isogeny. And one can check that this satisfies the condition of being a two cocycle. And while the cocycle depends on the choice of isogenies, but the cohomology class does not. Okay, the cohomology class is only depends on the isogeny class of the elliptic curve. And this cohomology class is very convenient for studying fields of definition of these elliptic curves up to isogeny because we can use it to state a version of Bayes' descent criterion for elliptic curves up to isogeny. So this characterizes for which subfields L of K, the elliptic curve E that we have can be defined over L up to isogeny. Namely, for which subfields there exists an elliptic curve E star defined over L, which becomes isogenous to our E when we extend scalars. And this happens even only if the restriction of this cohomology class to the Galois group of K over L is trivial. So now finding a subfield of K over which our curve can be defined up to isogeny is the same as finding a subfield over which the cohomology class becomes trivial. And for this, we need to adapt one of these results of Rivet. So he showed that the cohomology classes associated to non-CM Q curves always lie in the two torsion of the cohomology group. This is true for any non-CM Q curve, but this is not necessarily true for CM Q curves. We prove that it is true in this case, and here the key fact that allows us to prove this is that the square of E is isogenous to a variety which is already defined over Q. So this fact that the fact that the square of E is defined over Q, this implies that the cohomology class belongs to the two torsion of this cohomology group. But once we know this, we can follow Rivet again and use the fact that this cohomology group, the two torsion of this cohomology group has a very simple structure. If we define P to be the quotient of M star by plus minus 1, well, maybe here in general this should be the units of M, but let me assume for simplicity that the only units are plus minus 1. Then this is a free abelian group. It's a group of fractional ideals. And therefore, M star is isomorphic, I mean, non-canonically, but it's isomorphic to plus minus 1 cross P. And so the cohomology group with values in M star factors as a product of the cohomology group with values in plus minus 1 and the cohomology group with values in P. And now, the two torsion of the cohomology group with values in P, using the exact sequence associated to the square mapping in P, it's easily seen to be isomorphic to this group here, the Holmes from the Galois group of K over M with values in P mod P square. But now our cohomology class belongs, so it has a component in this group on the right, on this Holmes group, and this component is trivial when restricted to the subgroup generated by the squares, because these are Holmes to P mod P square. We're modding out by squares, so when restricted to the subgroup generated by squares, the component on the right, of our cohomology class is trivial, and then we have this result of Rivet that tells us that if the component on the right is trivial, also the component with values in plus minus 1 has to be trivial. So this means that C sub P is trivial when restricted to the subgroup generated by the squares, and if we call N the subfield corresponding to this subgroup, well, this will have exponent 2, and since the restriction of the class is trivial to this subgroup, by Bayes' descent, we deduce that there exists some elliptic curve defined over this subfield, which is isogenous to our elliptic curve. Okay, so this is how we finish the argument. Okay, so this was to prove that necessarily the imaginary quadratic field M has class group trivial C2 or C2 cross C2. And now the question is, of these possible M's, which ones do really occur? So we've seen in the theorem that some of them occur and some of them do not occur. So we need a method, we need a so a construction for the abelian surfaces that realize the m's that do occur, and we need a method to rule out the other m's, the ones that do not occur. Okay? So I will begin with the construction. For the m's that do occur, we will construct this abelian surface. And the method for constructing this abelian surface is going to be to use restriction of scalars. So we're going to obtain these surfaces as restriction of scalars. Let me begin with the really easy cases. So now the problem is the following. We start with this imaginary quadratic field M. And the easy cases are those in which the class group of M is either trivial or C2. And we want to construct an abelian surface over Q such that over Q bar becomes isogenously to the square of an elliptic curve E with Cm by this imaginary quadratic field M. Now, if the class number is 1, this is really very simple because we can take an elliptic curve E defined over Q which has Cm by M, and as A we take simply E cross E. So it's a surface, it's defined over Q, so we're done. If the class group is C2, if the class number is 2, then now we cannot find an elliptic curve defined over Q, which has Cm by Im, but we can find an elliptic curve over a quadratic field, okay? Because the field generated by the J invariant has degree 2, so we can take an elliptic curve defined over this quadratic field that has Cm by M, and as the abelian surface, we simply take the restriction of scalars from this to Q. So this has dimension 2, and over Q bar it's isomorphic by how the restriction of scalars is constructed. It's isomorphic to the product of E by its Galois conjugate. Okay? But this Galois conjugate also has Cm by the same imaginary quadratic field, and by this result I was saying before, we know that it's going to be Q bar isogenous to E. Therefore, A over Q bar is isogenous to the square of E. And we are done. We've constructed this abelian surface also in this case. Now, the case which is a little bit more difficult is when the class number is 4. So if the class group is C2 cross C2, now, okay, the field generated by the J invariant has degree 4, and when we take the restriction of scalars, it has dimension 4. So it's not an abelian surface. So we cannot use the same method. I mean, it doesn't work immediately. So now the idea is to choose this elliptic curve E appropriately in such a way that the restriction of scalars, which has dimension 4, is isogenous over Q to the square of an abelian surface. And if we manage to find an E such that the restriction of scalars breaks in this way over Q, then we're done, because this A will be the abelian surface that we're looking for. Okay. So how do we choose this elliptic curve? I mean, we have to find an elliptic curve in such a way that the restriction of scalars has this property. So we're going to take these elliptic curves to be gross Q curves. So Gross also studied, actually I think he was the first to use the term Q curve, but then later Ribet named Q curves, or he referred to Q curves to mean these elliptic curves isogenous to their Galois conjugates. But Gross, what Gross called the Q curve was something more restrictive to distinguish them from what nowadays people call Q curves. We will call these elliptic curves gross Q curves. So let me tell you what a gross Q curve is. So we have our imaginary quadratic field M. I'm going to denote by simply H now the Hilbert class field of M. So a gross Q curve is an elliptic curve E, which has Cm by M and is defined over the Hilbert class field of M. And it has the property that it's isogenous to all of its Galois conjugates, but the isogeny has to be defined over H, over the Hilbert class field. Okay? So now this is very restrictive. It is not clear that such Q curves exist. But we have this theorem of Shimura and completed by Nakamura, which characterizes precisely for which discriminants there exists gross Q curve. So it says that there exists a gross Q curve over H, over the Hilbert class field of an imaginary quadratic field M, even only if the discriminant of M is not of this form. Even only if it is not of the form minus 4 times a product of primes which are congruent to 1 mod 4. Okay, and well, so we're interested in the case of imaginary quadratic fields of class group C2 cross C2. So here's the explicit list. So these are the, I will call it D22. These are the, well, the absolute values of the discriminants of imaginary quadratic fields whose class group is C2 cross C2. There are, if I remember correctly, 24 of them. And of these 24 imaginary quadratic fields with class group C2 cross C2, the only one that is of this form is 340. Okay? But for all the other ones, we know that there exists a gross Q curve. Okay, so we'll have to deal with 340 in a different way. But for the discriminants for which we know that there is a gross Q curve, we're going to use another result of Gross. He proved this in his thesis. It's precisely what we need. So if we call script E the restriction of scalars of a gross Q curve from the, let's assume it's defined over the field generated by the J invariant. So the restriction of scalars, Gross computed the endomorphism algebra of this restriction of scalars, the endomorphism algebra over Q, and he showed that it's isomorphic to this twisted group algebra. So this is like the usual group algebra, but when you multiply the element on the basis corresponding to sigma with the element on the basis corresponding to tau, you get the element on the basis corresponding to sigma tau multiplied by the values of the cocycle associated to it. And well, now the idea is that if we manage to find a gross Q curve for which the endomorphism algebra is isomorphic to M2Q, then we're done, because this precisely means that the endomorphism algebra is isogenous to the square of an abelian surface. Okay? So now the question is to compute these endomorphism algebras of restriction of scalars of gross Q curves. And here we use a theorem of Nakamura. I mean, Nakamura gave a method for computing these endomorphism algebras precisely in this situation. Actually, he proved that, okay, so for each discriminant for which there is a gross Q curve, there are actually infinitely many gross Q curves, but they give rise to only 8 cohomology classes, so they give rise to 8 different endomorphism algebras for the restriction of scalars, and Nakamura gave a method for computing these cohomology classes. Okay, so what we did was for each discriminant in that list of class group C2 cross C2, except 340, for which there is no gross Q curve, we computed the endomorphism algebras of the restriction of scalars for each of the 8 representatives of Q curves. And well, this was extending a computation of Nakamura. He did it for a couple of discriminants. We did it for all the other ones. And what we found was that for the discriminants in this list, at least one of the Q curves has endomorphism algebra isomorphic to M2Q. So for the discriminants in this list, we've managed to find the abelian surface. And for the discriminants in this list, for these 5 discriminants, we find that all Q curves with all gross Q curves with Cm by these imaginary quadratic fields, the endomorphism algebra of the restriction of scalars is a division algebra. It's either a number field or a division quaternion algebra, and this means that the restriction of scalars is simple over Q and of dimension 4. Okay, so the first computation tells us that we've succeeded in computing the abelian surface for the discriminants in the first list, and for the discriminants in the second list, okay, we haven't found any abelian surface, and okay, for a while with Frances, we were trying to find another method for computing the abelian surfaces in these cases, but in the end we realized that, okay, maybe if we don't succeed, it's because the abelian surface does not exist in this situation. And this is precisely what happens, and so let me explain you how to prove that for these discriminants, the abelian surface does not exist. Also for minus 340, in which there is no Q curve, we can show that the abelian surface does not exist in this situation. Okay. So how do we do it to rule out the abelian surfaces in these cases? So now the problem is the following. We take an imaginary quadratic field of class group C2 cross C2, and we suppose that there is a gross Q curve, E over H. And we know that for this gross Q curve, the restriction of scalars does not have any factor of dimension 2, because we've computed all these restriction of scalars, and we've seen that they don't have any simple factor of dimension 2. And now we want to show that the abelian surface does not exist in this case, so we suppose that it exists. So we suppose that we have an abelian surface over Q such that over Q bar is the square of some elliptic curve with Cm by this imaginary quadratic field, and we want to reach a contradiction. And the contradiction is we're gonna obtain a contradiction from what we know about gross Q curves. So now, okay, once again, we have a control on the minimal field of definition of the endomorphisms of this A, and now it can be only C2 cross C2 or a hedral group, because we're already assuming that M has class group C2 cross C2, so the cyclic case does not appear now. And if the class group of K over M is C2 cross C2, then it's very easy to rule out the existence of this abelian surface, because now, well, the Hilbert class field of M is contained in K, but K and H have the same Galois group over M, so they must be equal. Okay, so K must be equal to H. And in this situation, the absolutely simple factor of A is actually a gross Q curve. It's isogenous to all of its Galois conjugates, and the isogenies are defined over H. But this is a contradiction with what we know about gross Q curves, because if E is a simple factor of A over H, well, there is a non-zero home from A to E, and by the universal property of the restriction of scalars, this means that there is a no-zero home between A and the restriction of scalars. But this is a contradiction because this restriction of scalars does not have any factor of dimension 2. So there cannot be any such homomorphism. Okay, so the case where this Galois group is C2 cross C2 is very simple. If the Galois group is a dihedral group, then, okay, we need another argument to rule out the existence of A. It gets a little bit more technical, but now what we'll use is that in this situation there exists an element in the Galois group of order 4 or 6, well, a certain element of order 4 or 6, and we're going to obtain a contradiction by looking at certain representations. Now, these are not actual representations, they are projective representations, and they are the following. So again, we suppose that we have our abelian surface over Q, that over K is isogenous to the square of an elliptic curve with Cm by M. Now, sigma, so E is isogenous to all of its Galois conjugates, but the isogeny in principle is defined over K, not necessarily over H. So this absolutely simple factor is not a gross Q curve in general, but we know things about gross Q curve. So we need to relate this E to some gross Q curve. So what we do is we take any gross Q curve over H. We are assuming that there is one. And this gross Q curve is going to be isogenous over Q bar or over some extension L of K to our elliptic curve E, to the absolutely simple factor. And then the representation comes from looking at these homes, the homes from the gross Q curve to A over this field L, or if you want, over the algebraic closure of Q. But this is not a Goulart representation in the sense that if we have a home from E star to A, when we conjugate it by an element in the Galois group, well, we have a home from sigma of E star to A, so the elliptic curve gets conjugated. A is defined over Q, but E star is not defined over Q. But E star, it's a Q curve, so we have an isogeny between sigma of E star and E star, so we can precompose with this isogeny and obtain again a homomorphism from E star to A. We can call this rho sigma of phi, so this is our representation, but it's not a true representation, it's a projective representation. So rho sigma composed with rho tau is not rho sigma tau, it's rho sigma tau multiplied by a scalar, and actually the scalar is precisely the cocycle of E star as evaluated at sigma and tau. This is a projective representation. We call it a C sub E star representation just to remind ourselves that the scalar that appears is this cocycle C sub E star. And the key fact here is that, well, this is not a this is not a true representation, and its contragradient is also not a true representation, it's a projective representation. But when you tensor these two projective representations, since the scalars appearing in the contragradient representation are precisely the inverses of the cohomology class, while the tensor product is a true Galois representation, and it's actually isomorphic to the representation afforded by the endomorphisms of A defined over K. And using this, that this tensor product is a true representation, so we can say things about the trace of this representation and etc. On the left-hand side, we have something that has to do with the values of the cocycle of E star. We can prove that the cohomology class associated to E star, when evaluated at this element of order 4 or 6, it's plus minus 1. And this is a contradiction with something that we know about gross Q curves, because we know that gross Q curves, they have the property that when you evaluate the cocycle at a non-trivial element in the two coordinates, then you get plus minus a proper divisor of the discriminant of M. So this is a contradiction, and this is what rules out the existence of the abelian surface in this case. Okay. So this was for the case where there is a gross Q curve, and we need an extra argument to rule out that exceptional discriminant minus 340. But okay, this can also be ruled out. Okay, so this is more or less the end of the argument. And just to finish, let me remind you once again what we proved. We proved that this set A to 1 split of Q-bar endomorphism algebras of geometrically split abelian surfaces over Q consists of these 92 algebras. And at this point, there is a natural question, what we think is a natural question, which is, okay, which of these 92 endomorphism algebras arise actually from Jacobians of genus 2 curves defined over Q? And so this is precisely the content of Francesc's talk on Thursday. He will explain this to us, how many of these arise from Jacobians of genus 2 curves. And the spoiler at this point that I can make is that not all of them arise as Jacobian. But I leave it to Francesc to tell you exactly which ones appear and which ones do not appear as Jacobians over Q. Okay, thank you very much for your attention.
So, thank you. Oops. Can you hear me? No, I'm not sure. Sorry. Okay, now it should work. No, still no. Yeah, okay, great. Okay, thank you. Are there any questions? Yes.
So I had a question about something on slide 4.
Okay, maybe it's faster. Yes.
Or maybe it was slide 3.
3, okay.
Nope. Was it 5
2?
maybe?
No, 5?
Well, it was around here. Sorry. Oh yeah, there it was. Slide 4. Sorry, I see it now.
Okay.
Yeah. So the 19 possibilities for the CM field. So I suppose that 19 should be 13, but also these 19 CM points corresponding to the 13 fields in Murabayashi Umegaki, they are with CM by the maximal order. And you want to know everything, right? Also, if there's maybe not CM by the maximal order, but only
Yeah. We're interested in everything, okay? But now I don't... You say it's 13 instead of 19?
Yes.
Okay, because there are... okay.
So 19 is a number of surfaces that have CM by the maximal order.
Okay.
They correspond to 13 fields, because some of the fields appear twice. But Murabayashi Umegaki were only interested in the maximal order, and you were interested in the,
yes, that's right.
in the general case. I don't know how you went from the...
Yeah, maybe you're right. Maybe the result is explicit only for maximal order, but
But
yeah.
you can get what you say there if you combine it with some results of your session chair. Actually.
Okay.
So, okay. Thanks.
Thank you.
So, great result on the endomorphism algebras. Can you say anything about the endomorphism rings? Have you thought about that at all?
We thought a little bit, but I cannot say anything because, yeah, all our results, I mean, the key is this, using this cohomology class that controls the field of definition up to isogeny. But then, for the endomorphism ring, yeah, we don't know. No.
Any other questions, comments, anything? I have a question about this simpler case, the case that you, I think it's slide 5. Right, the second case. So you use this Fittek, Edlaya, Rotger, Sutherland results. So is that only for abelian surfaces, or?
I think so. Well, the authors of this result are in the room, but I would say it's only for abelian surfaces in this precise situation in which one of the factors has CM, and they are non-isogenous.
Yeah, I was curious because if it is also true for higher dimensions, you can just, yeah, have simpler
No, I don't
classifications
think so.
in that case. Okay.
But,
Any other questions, comments? Okay, let's thank Xevi again.
thank you.